I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
Picking up some dust.
In the 1960s, an impossible dream came true when human beings walked on another world.
The Eagle has landed.
In all, 24 Americans went to the moon. But it took an unseen army of over 400,000 engineers and technicians to make it possible. This is the story of the men and women who built the machines that took us to the moon. During the late 1950s and early 60s, the Cold War between the Soviet Union and the United States took an ominous turn which shocked the American people.
Wait a minute. They put a satellite in orbit around the Earth? I think I said something like, golly gee, son of a gun. I didn't really say it that way, but similar.
A group of us actually climbed to the top railings of the test stands and watched Sputnik go over as a white dot going across the sky like a meteor.
And of course, all it was doing was going beep, 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 beep. But hey, they put it up there, you know.
The new strategic high ground was space. And the Russians continued to chalk up an impressive list of firsts.
They had launched the first man, Yuri Gagarin. They had launched the first lady, and they were really in all areas way ahead of us.
So we said, we better get cracking.
The Russian space program called for a response. In May 1961, President Kennedy galvanized the American people with an audacious challenge: to reach for the moon.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win.
I was so proud of him, I was jumping out of my pants, practically. I mean, and I was so excited because I knew I was going to be able to be a part of it.
I didn't realize the magnitude of the challenge or some of the technical requirements, but I still felt that, you know, we could do anything at that time.
We were all young. We didn't know what failure meant, and we knew we could do it.
Reality sets in for a moment and say, well, how are we going to do that? 10 years? That's a short time. And so it was a mixture of exhilaration and maybe even depression to think about how you're going to do this.
To many, Kennedy's goals seemed almost impossible. But the president knew more than he was letting on. The key to his confidence lay in a small town in Alabama.
In the 1950s, Huntsville was a sleepy little town. When I first came here, the population was about 18,000 people. Soon, we newcomers outnumbered the old-timers. It was a happy time.
Among the newcomers was an unlikely group of people with a valuable set of skills: German rocket engineers. Led by Werner von Braun, the Germans had already mastered the basics of rocket propulsion. During World War II, they built the V-2, the world's first ballistic missile. Engineer Conrad Dannenberg.
When we came to the United States, we brought with us the V-2, all the plans for the V-2. The people in the United States were very impressed by the capability of the V-2. This technology was very important for the growth of the space program because these engines are more efficient, they can be controlled, and you really have a capability to work with your engines during your flight.
The German people who came over were indeed very skilled people. They were, all of them, dedicated to rocketry and wanted to continue that, not from the standpoint of having rockets to launch on enemies, but the whole thing behind their thoughts was going into space, going to the moon.
With the Russians leading the space race and America desperate to catch up, von Braun saw an opportunity to fulfill his lifelong dream.
Von Braun was always thinking in the back of his head, we're going to the moon. That's what he wanted to do. And it infused everybody. We all wanted to go to the moon. All you had to do was talk to him 5 minutes and you were ready to go. He was very charismatic. You know, he could sell a refrigerator to an Eskimo.
Von Braun turned his persuasive skills on the new president.
And that, of course, was what eventually led President Kennedy to announce a trip to the moon. I'm sure he had been influenced by Wernher von Braun.
Even before Kennedy's announcement, von Braun's team was designing a family of rockets they called Saturn. First on the pad was the Saturn I, almost 200 feet tall and with a thrust of 1.5 million pounds. When it lifted off, the engineers could not suppress their excitement.
Ignition. Engine running. Thrust commit. Launch commit. Liftoff.
The Saturn I successfully demonstrated the key technique, which would be vital in building a much larger moon rocket. This was the concept of staging, in effect stacking multiple rockets one on top of the other.
If you tried to go to orbit with all one stage, the amount of fuel and the size of the engines required would have to push the entire weight of that first stage to that full velocity. They learned that through analysis that the best way to do it was to get to orbit using multiple stages. So that the first stage would give you a certain amount of what they call delta V, change in velocity from 0 to a certain speed, and then you would drop off that whole stage, all of its tanks, all of its engines, and all the weight associated with it, so the second stage had much less mass to push.
But to go beyond Earth's orbit would require more than 2 stages.
And when you do the calculations, the most efficient way to build a moon rocket, one to get to the moon, turned out to be a 3-stage vehicle.
On paper, the 3-stage concept looked like this. Stage 1 would have a cluster of 5 engines, the likes of which had never been built before. Called the F1, on liftoff, each one would need to burn almost 3 tons of fuel a second, just to lift the enormous rocket off the pad. Stage 2 would also cluster 5 engines, the smaller J2. The third stage would use a single J2 engine, which would have to fire more than once, to place the elements of the Apollo spacecraft first into Earth's orbit and then on a course to the moon. When assembled, it would be the largest flying machine the world had ever seen. On paper, the Saturn V was capable of taking men to the moon. But could drawings be successfully turned into reality? The first stage of the giant rocket would be the largest. It needed to provide the initial thrust to lift the vehicle off the pad to a height of around 35 miles. The cluster of F1 engines designed to do this would require a huge leap forward in technology. Although they'd only burn for 2.5 minutes, the pipes and valves would have to withstand immense pressures and temperatures, If successful, it would be the largest liquid-fueled engine ever flown. To oversee its production at the newly formed Marshall Space Flight Center in Huntsville, von Braun turned to a young engineer called Sonny Morea.
He gave me the responsibility for a $1 billion program. $1 billion in those dollars, not today's dollars. And he picked on this young guy who was 28 years old, didn't have very much experience, and gave me the challenge of being the manager of that program. Greatest decision that I think the man could make.
Building such a large rocket engine would also require a test facility on a similar scale.
When you fire the first stage engines of the Saturn V, you develop 7.5 million pounds of thrust. That's tremendous kinetic energy coming out of those exhausts. And of course, you couldn't let it project the exhaust directly in the ground because pretty soon your test stand would fall over. So instead, you use a flame bucket to catch the exhaust gases and then deflect them outward.
The huge amounts of energy unleashed posed problems for those living nearby. Under certain weather conditions, the shock waves from the engines would become trapped close to the ground and travel a long way cross-country.
In fact, the first few firings, we were breaking windows in downtown Huntsville, which is over the hills to the rear here, and we knew we couldn't keep doing that very long or we're going to lose the support for the space program in the city of Huntsville.
But the tests had to continue, and they soon revealed something unforeseen was happening as the fuel burned in the combustion chamber.
One of the big problems we ran across was the problem of combustion instability. And by that, we were dealing with rotation of the flame of the burning process within the thrust chamber of like 2,000 cycles a second.
The rapidly rotating flame could destroy the whole engine in a matter of seconds.
It was a showstopper. There was no question about it. We had to find a way to make the engine run stable. The thing that was so overwhelming to me was that unless we solved this problem, we would not be going to the moon with a man.
Combustion instability took thousands of man-hours and many agonizing months to solve.
Keep in mind that back in those days, we were designing rocket engines basically with slide rules.
The answer lay in the way the fuel was injected into the combustion chamber.
The solution to the problem is shown by that series of copper baffles that you see on the face of the injector. And that particular arrangement baffled the oscillations so that we now had stable combustion. So it was a very nice, unique solution to a very serious problem that was a big showstopper in the program, had it not been solved.
With the construction of the first stage well underway, the building of the second fell to the engineers at North American Aviation in California.
Stage 2 was a technical challenge of the first order. We had some unique manufacturing problems, we had interesting design problems, and it was probably the biggest challenge of the Saturn V.
The main headache for the Stage 2 team was that the Apollo spacecraft, the command and lunar modules sitting on top of the Saturn V, kept getting heavier as their designs evolved. That inevitably meant that the rocket below them had to be made lighter. One of the engineers feeling the pressure was George Phelps.
When they gave us a weight reduction problem, we said, well, we'll take some out of the first stage, some out of the third stage and the second stage. No, the first stage is too far along, and so is the third stage. And so we got to take it out of the second stage.
A radical solution was needed to shed weight from the second stage. Normally, 2 separate tanks stored the liquid oxygen and liquid hydrogen fuels, with a temperature difference between them of over 120 degrees Fahrenheit. At both ends of each tank was a strong, relatively heavy, dome-shaped bulkhead.
So to save weight, somebody came up with the idea to eliminate one bulkhead. This was the biggest, I think, the biggest challenge on that stage, to have one bulkhead to separate the 2 fuels.
The stage would now have only one tank, and the fuels would be separated by just one divider, known as the common bulkhead. This arrangement had a double benefit. It got rid of one of the heavy bulkheads, and it reduced the overall length of the stage. But it also meant that 2 liquids at vastly different temperatures were right next to each other.
And we had a divider that was about that thick. That was the most difficult problem that we had to solve, but we did it, because engineers can just about do anything.
But the greatest temperature problem was not keeping the intensely cold liquid fuels insulated from each other. It was keeping both of them from boiling in the hot Florida sun.
We insulated the liquid hydrogen tank in the early days with a honeycomb insulation. We put it on in big vacuum chambers, and we sucked the honeycomb down onto the metal, pulled it tight, and let the adhesive set. But all through the early stages, we had problems with the honeycomb insulation popping off the vessel.
The engineers realized they were doing something wrong. To fix it, they would need specialist help.
We were manufacturing the vehicle at Seal Beach in Southern California. And Seal Beach is a big surfing town. And we found that the surfers had been using honeycomb insulation to make their surfboards, and they were very skilled at using it. And we finally started hiring the surfers, and they did a great job with it. The only downside of those guys was that when the surf was up, there was a big absentee problem. They were out there doing their trick. But they were a great bunch of guys, and they really brought a unique skill to the space program that I don't think we appreciated at the time until it was pretty well over.
The Saturn V's third stage was also under construction in California, at the Douglas Aircraft Company. The third stage had the job of propelling the Apollo spacecraft out of Earth orbit on a trajectory to the Moon. Among the engineers working on it was Don Brinka.
Well, the third stage for us at Douglas was one of the biggest stages we've ever made. It was 22 feet in diameter.
As with every part of the Saturn's hardware, testing was critical in ironing out the problems which had been overlooked.
We were preparing to test the third stage at our facility, and I was a director of test operations. I was responsible for all testing. I was sitting at my table in the control room, monitoring all the other events that were going on and watching for any problems and following the countdown. The stage was fully tanked and fully pressurized. We were progressed satisfactorily up until the point moments before ignition, and when we had a component fail. It was not hard to tell something was wrong. The whole blockhouse shook, everything rattled, and the screens all went white, and so we knew there was a major calamity. It was kind of a heart-stopping moment when that occurred, and we knew that the work was cut out for us to get this one resolved.
Once the fire was out, the team began a painstaking investigation. Attention soon focused on a metal sphere which had held pressurized helium.
In the process of going around and looking in the test stand, we noticed that one of the spheres, we could only find a half of it.
And that was an important clue as to what had caused the explosion.
So that's when we zeroed in on the conclusion that the sphere came apart. So then we did a series of tests and found that the wrong material had been used to weld the spheres together, and found that under pressure it would come apart. It was a real exercise for the engineering staff, very stressful, long hours, because you wanted to find it as soon as possible. We had a flight stage failure, and without that stage, you would not get to the moon.
Douglas wasn't the only company having problems with their welds. Welding was the best method for constructing the Saturn V. It was far lighter than using rivets, but thousands of feet of welds were needed, and welding was proving a real problem for engineers like Bob Schwinghammer.
We could not weld it. For weeks and weeks we could not weld it. And you know, they kept telling me, if we don't solve this problem, there won't be a Saturn V.
In order to save weight, we varied the thickness of the metal from the top to the bottom. And so to weld two pieces together of different thicknesses gives you a different heat flow pattern. It makes the welding all the more difficult.
And what we had to do was tear into the welding machines and redesign them ourselves. You know, one thing after another came up, and there were problems you had to solve, and they were new things. That was unplowed ground. Other people had never had to do that, and so we found out and figured out ways to do it.
With time and perseverance, the rocket engineers solved problem after problem. However, time was a luxury the Apollo program did not have. Early in the Apollo program, NASA realized it would have to drastically accelerate the development of the Saturn V in order to meet the deadline of placing a man on the moon by the end of the decade.
NASA headquarters had made the proposal to skip one of the missions that von Braun had initially proposed, and to go what later on became as the all-up concept.
And what that meant was that we take all the stages and we take them to Cape Kennedy, we stack them, pile them up on each other, and then we would run the test.
Well, the risk of all-up testing is that if anything failed, any part failed, we would lose the vehicle.
November 9th, 1967. Finally, after more than half a decade of technological achievement, the Saturn V was poised for its first unmanned all-up test. The flight would be known as Apollo 4.
Apollo 4 was a tense time because those of us who were working on the individual stages were not sure that if we didn't do the individual stage tests at the time, something might go wrong.
Testing to date had been successful, and so we had reason to believe that everything would work. But always there's a little something that happens you never know about.
I looked at it and I remember thinking, you know, my God, we've done this. We've gotten it built and we've got one ready to fly. It's probably got 1 million pieces in it, and they all got to work at the same time.
Liquid hydrogen tank in the second stage now pressurizing. T-minus 60 seconds and counting. T-minus 60.
I was in awe of what was going on, because I realized that not only was my F1 engine so important, but so many other systems went through that same sort of experience. They all had their major unknowns. They all had their teams that had to do their jobs perfectly, or that vehicle would not work.
T-minus 50 seconds and counting. We have transferred to internal power. The transfer is satisfactory.
As it comes up to ignition point, you're trying to run over in your mind all the things that you thought might need checking, again, well, I think this is okay, and yeah, it has to be. We checked it so many times.
We knew the countdown was going down. We knew what time they were supposed to launch. So we were all just transfixed on the launch pad.
15, 14, 13, 12, 11, 10, 9. Ignition sequence starts. 5, 4. We have ignition. All engines are running. We have liftoff. We have liftoff at 7 a.m. Eastern Standard Time. The tower has been cleared. The tower has been cleared.
You see it move off very slowly. Oh, what's wrong? It's never going to go. Come on, go, 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 go.
You want to coax it, get off of there.
You say, my God, that's, thousands of tons, and it's moving so slow you think it's going to fall over.
Shock wave is progressing across the water, coming towards you. It's pretty impressive,
I had never felt this much power and energy from that distance.
We were going like, the ground was shaking like an earthquake in California.
It was absolutely incredible. You thought that you were going to be knocked over with the power of that.
I did hear women saying, oh, oh, oh,
ooh, ah, and then clapping.
It was the dawn of a new era in spaceflight. With 5 engines guzzling 15 tons of fuel a second to generate 160 million horsepower, the 6.1 million pound Saturn rocket soared skyward.
I was, so nervous when the ignition was on the first stage, took off, and it fired properly, and that was wonderful. And then all I'm worried about is what are we going to do after the first stage burns out? Is ours going to start? And so we're watching the data, and we're watching the data, and we're watching the data.
I don't think I breathed for 8.5 minutes.
We drop the interstage, which is pretty neat, and we ignite the J2 engines, and they all come up to thrust. And we say, it's working, it's working, it's working.
Phew. And that's what we thought, phew.
And we ran out of fuel, and the fuel cutoff sensor said, we're out of gas. And then the S-4B ignited, and it took off. And to me, I was all over by that time. My part was done.
Apollo 4 had been a near-perfect flight. Suddenly, the president's goal seemed much closer. After the success of Apollo 4, the Saturn V's second all-up test, Apollo 6, was set for 5 months later, in April 1968. The men who had built her felt confident.
We have liftoff. Liftoff at 7 a.m. Eastern Standard Time.
We figured, let's just sit back and relax, because there's no other problem that could occur. I mean, we flew it, we did an all-ups test, and it flew perfectly, and so no problem.
Mark, 1 minute, 25 seconds. Pass through max Q, still looking good.
As Apollo 6 lifted off the pad, the mission looked like it was going to be another textbook performance.
Intermittent at this time, standing by.
But less than 2 minutes into the flight, things started to go seriously wrong.
The engines were firing, and they were vibrating. We expected them to vibrate, and they're attached to a thrust structure. And the thrust structure was being excited by the engines, and it was vibrating.
Within seconds, the vibration strengthened and began to oscillate up and down the entire length of the rocket.
If you were unlucky enough to get the oscillation in the thrust chamber tuned to the oscillations in the pipe itself, then they would tend to amplify each other.
The rocket was experiencing a phenomenon called resonance.
An example of that is the opera singer in the wine glass, where she hits a note that's exactly the same frequency that the wine glass will tingle at if you tink it. And if left to its own devices, the resonance can, in essence, destroy whatever it is that's resonating.
And all these vibrations came together all at once and created a humongous vibration that moved all the way up to the spacecraft. Had there been astronauts in there, we would have had to abort the mission because of that vibration level.
As the first stage finished its burn, the vibrations stopped. But the problems with Apollo 6 were just beginning.
Flight Econ. The water boiler's okay and the cabin's holding in 6.
Roger, GNC, how are you?
Oh, we're looking pretty good last time we had data here, Flight.
4.5 minutes into the Stage 2 burn, Mission Control noticed a J2 engine begin to falter.
All we knew was that the chamber pressure for one of the outboard engines was deteriorating, was dropping off. We didn't have any idea as to the cause, but it was failing, and the chamber pressure started to oscillate, and finally the engine shut itself down.
Within seconds of the first engine shutting down, another J2 engine cut out.
Flight booster, go. We've lost engine 2 and engine 3.
You've lost the engines?
That's affirmative. Roger.
And therefore, we had only 3 engines on the second stage, whereas we required 5.
Propulsion guys were saying, goodness sakes, golly gee whiz, what happened? Sorta.
I think we have 2 engines out. Don't get nervous.
Roger, I understand.
It seemed the unthinkable was about to happen. They were going to lose the Saturn altogether.
The stage then, instead of flying its original trajectory naturally with 2 engines out, it keeled over, and eventually, running about parallel to Earth, it righted itself as the remaining engines gimbaled to try to get it righted again.
Flight booster 2, we seem to have good control at this time. Roger. Guidance system perform anomaly, Flight. Roger, you sure, booster?
It was a close call, but Apollo 6 managed to limp into orbit.
Roger.
Immediately, the head scratching began.
We were highly disappointed and knew that we had a lot of work to do to diagnose the problem and resolve it before the next launch.
The resonance effect proved relatively easy to fix.
What we did was, in the subsequent stages, we put what we call an accumulator in there, which is nothing more than a shock absorber, like you have in your car. So we put the accumulator in there, which is a pressure vessel, and solved that problem.
But what about the second stage? Why had 2 engines suddenly failed? Sifting through the data, the fault was narrowed down to a small flexible pipe which fed fuel to the augmented spark igniter. The spark igniter was a crucial part of the Saturn V engines. Like a spark plug, it ignited fuel from the flexible pipe, which in turn lit the main engine. During the flight of Apollo 6, the pipe feeding fuel to the spark igniter had ruptured. Without an ignition source, the J2 engine began to splutter and then shut down altogether. It was a failure the engineers had never seen before, despite all their tests.
When you tested it on the ground, ice would form because the hydrogen was so cold, and freeze and make the line actually be a stiff line.
But as one flies into space, and eventually there is no moisture, and therefore there's no ice to form and nothing to dampen the vibration of the spark igniter.
The vibrations had led to the line flexing and rupturing.
We figured out if it's rigid on the ground and didn't have to be flexible when we're flying, and so we put a solid pipe in, and that solved the problem.
But why had the second engine failed so abruptly?
The fact that the second engine shut down all by itself with no other indication was a complete surprise. We had no idea at the time it occurred that there was anything wrong with the way it was operating. Actually, there was nothing wrong with the way it was operating.
The reason for the failure was somewhat embarrassing.
The computer sensed that there was a problem with an engine, so it commanded that engine to shut down.
But the signal never reached the faulty engine where the pipe had ruptured. Instead, it shut down a perfectly healthy engine.
We didn't realize, but the wiring for the two engines had been crossed.
A simple mistake had almost wrecked the flight of Apollo 6, but at least the fix was easy.
And so what we did was we made sure that the wirings were shortened so that they couldn't cross. So that's what we did.
The near failure of Apollo 6 came at a bad time. In 1968, the possibility of America being upstaged by the Russians was still very real. NASA felt they couldn't delay any further. The third flight of the Saturn V would carry astronauts not to orbit the Earth, as everyone had expected, but to orbit the Moon. In December 1968, with little more than a year to the end of the decade, the race for the Moon was intensifying. Despite the near loss of Apollo 6, NASA was pushing ahead with Apollo 8, the third flight of the Saturn V and the first to carry a crew.
Well, Apollo 8 launch was a bold move again because there's always a possibility of another problem occurring, but NASA felt that they were ready for it. We felt we were ready for it. So I believe it was a step that had to be taken if we were going to get to the Moon.
We were determined to make the Apollo 8 flight, and we put lots and lots and lots and lots and lots and lots of hours in order to meet that flight.
I recall I'd leave for work about 6 in the morning, and I'd get home at 8 or 9 or 10 o'clock at night, and my kids were asleep by this time. My wife wasn't speaking to me probably. I think most of the wives felt that we had a mistress, and we did, and it was a launch vehicle.
With the years of toil and testing behind them, it was time for the engineers to place their vehicle in the hands of the astronauts. Frank Borman, along with Bill Anders and Jim Lovell, were the crew selected for the flight of Apollo 8. For the engineers, now came the realization that human lives were at stake, and for some, it was an uncomfortable prospect.
When we got right up to the point of launching astronauts, then all the fears and worries really came into existence. You worried along the way, but you realized that no human life was at risk at that moment. But suddenly, when you're coming up to your final flight review time, you realize that there were 3 lives that were depending on whether you and your team did their work properly and understood what they were doing. And I'll never forget the one meeting that I had where Frank Borman was in the meeting with us. And I was suddenly overwhelmed by the fact that we were now committing the lives of these 3 astronauts. And so during my presentation, I may not have come over exactly overconfident. And Frank Borman picked up on that. And as we broke for lunch, he grabbed onto my shoulder going out the door of the room, and he said, "Sonny," he says, "you guys have done the best job you possibly can do. We followed the program. We understand what's going on. We know what the risks are, and we're prepared to take them. Don't sweat it. We're ready to go." And that made me feel great. That was probably the greatest moment in my life during that program.
We have liftoff. It's 50 seconds into the flight. Apollo 8, you're looking good.
I remember when I drove away from the Launch Control Center after the launch and I looked out at the pad and it was gone. And I actually felt like I lost one of my kids. It was just, a tragic loss to me. And I never felt that way about any of the subsequent launches. But that one, a piece of me went up and went downrange and fell in the Indian Ocean somewhere.
After the first and second stages were spent, the astronauts now relied on the final third stage. Its first task was to place the Apollo spacecraft in a parking orbit 215 miles above the Earth.
Apollo 8, Houston, you are go, over.
And then to send them to the moon.
As the third stage was orbiting the Earth and the checkouts were in process, the engine had to be reignited. That's called translunar injection. And that was very tense because the whole program depended on that engine starting appropriately.
TLI was always a tense time for the entire team. And yours truly certainly was an intense time because we were counting on that engine igniting precisely at the right time and burn precisely as long as it needed to burn to give us the precise velocities that we needed to reach the moon properly.
Apollo 8, you are go for TLI, over.
With the translunar injection burn successfully completed, the crew began the 3-day cruise to the moon. The job of the Saturn V was over. For each 2-week Apollo mission, the rocket fired for less than 15 minutes. But for those involved in building it, the journey had taken the best part of a decade, and those years would remain with them for the rest of their lives.
I'm 94 years old right now, but I still look fondly about the good old days when we worked on the Apollo Saturn program with Werner von Braun. It was one of the highlights of my career.
Some of the problems that we solved and the solutions were so elegant. It just brings tears to your eyes sometimes when you think of, well, that was the problem and this is how we solved it, and we solved it really well.
It was such an incredible thought that man could leave the planet and actually go to the moon that man has been looking at for thousands of years, and then you say, we're up there.